Okay, this is part of a series of lectures on security, and this lecture focuses on encryption. The main areas we will look at are before electronic communications, some examples of codes, a few fundamental areas, key-based encryption, cracking the code, and brute force. Then we'll look at block or stream encryption, some of the main private key methods, encryption keys, how we pass encryption keys, public key encryption, then onto one-way encryption, encrypting disks, and then finally on to PGP encryption. Okay, so let's look at a basic introduction to encryption. The four characters that we will look at in this series of lectures are the good people, who are Bob and Alice, and Bob and Alice are trusted. Unfortunately, we also have Eve, who in this case we'll define as an intruder. In this series of lectures, we never actually define Eve as a hacker. A hacker often implies guilt, so we will refer to Eve as an intruder. Along with this, as we'll find, we need a third-party trusted person called Trent. Trent will be seen more in the authentication than in the encryption part. And basically, Bob and Alice are good, and the intruder is not trusted. The problem that we have is that internet communications and network communications are an extremely complex system. We have many applications going on, we have many servers, many devices, many users. Each of these users could be mobile. So we can see in this case we might have switches and firewalls, intrusion detection systems. We have all our servers over here on a demilitarized zone. We have firewalls, servers, and so on. Along with this, we have many different protocols which are running. And the key objective is to make sure that Bob and Alice can communicate securely without Eve viewing the communications or modifying them in any way. Unfortunately, the protocols that we've created to allow the communications are typically text-based and are seen as being insecure. So the problem that we have is that we're moving away from these insecure protocols such as HTTP, Telnet, FTP, POP3, SMTP and DNS into the new domain, which typically involves some sort of security, either in terms of encryption or with integrated authentication. So these new protocols typically involve encryption and also involve some form of authentication. As we'll see, authentication is just as important as security. And the main people that we'll come across when we look at these methods include Whitfield Diffie, who came up with key interchange and could see the day when public key encryption could happen. We'll look at Revest, Shamir and Alderman, who came up with a public key encryption method called RSA, named after themselves. We'll also see Ron Revest, who advanced his work on to encryption and also into hashing methods, and Phil Zinnerman, who created the PGP encryption method. Okay, so what were some of the methods that were used before electronic communications? Well, we've all seen examples of microfiche, where secret messages could be stored in very small areas. The Indians used smoke signals. Carrier pigeons have been used extensively, and in the Second World War, the Navajo words were used to pass secret codes. Along with this, we can see quilt patterns that were used by American slaves, actually described a map of how to escape. So what were some of the codes that were used to keep messages secret? Well, one method that we can use is to use an encoder on one side and a decoder on the other side. It's then up to Alice and Bob to define these encoder-decoder and then to keep that secret. As long as Eve doesn't know what the algorithm is, then Bob can encode his message in a secret form. We typically call this a ciphertext and this a plain text. Pass it, and Alice knows how to decode it. One of the first examples of this was the Caesar code. With the Caesar code, the letters of the alphabet are moved a certain number of spaces. In this case, we can see the letters have been moved 2 spaces to the right. So the message that comes out is encoded in some way. So in this case, R, capital R, is a T, and F is an H, C is an E, so we see the first word is the, a Z is a B, so the boy stood on the burning deck should be the message here. To our eyes, this seems a fairly simple code, but at the time it was fairly secure. Overall, as there are 26 letters in the alphabet, there are only 25 code mappings, so it's fairly simple for someone to be able to decode this message. A more advanced version is to scramble the alphabet up. In this case, the letters have been scrambled, so a Q in this case is a T, a B is an H, a C is an I, and a T looks like it's going to be an S. A T is somewhere. T is an S up here. And the advantage with this is that we now have 4 and 26 zeros, so it's 403 million billion codes. So it looks as if this is a fairly secure coding system. Unfortunately, the English alphabet has a varying probability for each of the letters. For example, an E is the most probable, and in UK English, a Z is the least probable. Along with this, there are 2-letter occurrences, 3-letter occurrences, and words. So it is then possible to look up the probabilities of each of the letters and then to try and match them with the cipher code. So in this case, we probably would find that the letter E in this case is coded as an A, so we can see it is a highly probable letter, so we could probably guess that that was an E. So that method suffers greatly in that the probability is seen with inside the actual ciphertext. An improved method is one that has a moving mapping. In this case, we define a secret key code, in this case green, so then the mapping will move around from G to R to E, E again, and then to N. So the mapping will go, in the first case, from A to this line here. So an A would be mapped as a G, and so on. So as we build this up, the first letter here is an H, and we go to row G, which is this row here, and that gets mapped to an N. Next, we have an E, and the row is R, so we have a V here. Next, we have an L, and we're on the E row, so an L in this case becomes a P, and so on. So this is an improved method of reducing the standard occurrences of letters. It's not perfect because it will recur. An improved method on this is to map each of the letters to certain codes. The higher the probability, the more codes that will be used for the letter. So in this case we can see that E has many codes associated with it and Z has very few. Each time an E occurs, a new code or a different code is taken for it. 25 first time, 26 second time, 28. So it will now be very difficult to analyze the numbers that appear, as they should all be equally probable. Okay, so let's look at some of the fundamentals involved in encryption. What we have, we typically define as standard text or plain text. This is typically defined in ASCII characters. So we would typically view them as letters, A, B, C and D, but they are interpreted by the computer in some form of byte format. So in this case, the letter A in ASCII is represented by 10000001, a B, C and D, and so on. When we typically encrypt the binary stream. So the binary stream is then encrypted into a ciphertext. It is very difficult for humans to actually be able to view ones and zeros, so we typically view it in terms of either a hexadecimal format or in a base 64 format. For hex is a convenient way for viewing binary. In hex, we take 4 bits at a time and we convert that into a hex character. So in this case, 1001, we look up the binary table and we find it here. So the hex character for that is a 5, second one is an E, and so on. So hexadecimal is a convenient method to represent our bit stream, in that we can very quickly convert these values because we only have to remember 16 different characters. The other way that can be used is a standard way of representing binary in messages such as email messages, and that is base 64. With base 64, we take 6 bits at a time and we convert that into a character. So we can see here the first character is, the first 6-bit stream is 010111, and that is equivalent to a 1, 2, 4, 7 and a 16, which is 23. So 23 represents an X. So this is defined as base 64 format and is a useful way for actually sending binary information over standard text-based protocols. The other 2 operators that we'll see in encryption are fairly simple ones, and this is where we take bits together, line them up, and then we use the exclusive OR operator. With exclusive OR, a 1 and a 1 gives us a 0, and a 0 and a 0 gives us 0. A 1 and a 0, or a 0 and a 1, gives us a 1. So we can see in this case a 1 and a 1 gives us 0, 1 and a 0 gives us 1, 0, 0 gives us 1, 0, 1 gives us 1, and so on. The great advantage with exclusive OR is that we don't actually lose any information when we exclusive OR something with something else. Typically, we can inverse the operation by exclusive ORing it again with the same value. The other operation that we use is a shift left, rotate left, or rotate right. In this case, we have rotate left 2 spaces, so all the bits go 2 spaces to the left, and then the bits that come off the end go into the start. So we can have rotate left, which goes that way, or a rotate right. Each time the bits come off the end and go on the other side, and that way no information is ever lost. Okay, so what is key-based encryption? Key-based encryption is the alternative to using an encoder and a decoder. With this, the major problem with having an encoder and decoder is that we don't actually know at any time if Eve has actually gained the encoding-decoding algorithm. So an improved method is to have a standard algorithm that everybody knows about. And then what we do is use a special key to apply to the algorithm, and the key is fairly difficult to find so that Eve cannot find the key. The key could be shared between Bob and Alice in this case and kept secret so that Eve cannot find it. So in this case we take the plain text into ciphertext. Eve doesn't know the key, even though she knows the algorithm. It's sent to Alice, and Alice can then decrypt it with this special key. The main methods, as we'll see, are defined as symmetric encryption. With symmetric encryption, Bob and Alice use the exact same key to encrypt and then to decrypt. We'll also look at asymmetric encryption, where we use a different key to encrypt and to decrypt. And then there is a special encryption method called the one-way hashing, in which we can transform a message into what's defined as a hash message. The methods that we'll look at here for private key include RC2, RC4, DES, 3DES and AES. For public key, we'll look at RSA. For hashing, the two main methods are MD5 and SHA-1. So the key thing we need to know is that how safe is our key? How big should our key be? How complex should it be? So let's look at an example where we have 4 notches in a key, and the notches can either exist or not exist. How many keys can we have in total? Well, we can have 2 to the power of the number of notches, or in this case 16 different keys. If we represent this in binary format, a key without any notches is all zeros, and a key with all the notches is all ones. So we can see here that it wouldn't be too difficult to find the key because there are only 16. So it is obvious to keep something secure that we need to limit the number of keys. We need to maximize the number of keys that are available. Just to show you the scales involved of these, let's say that each one of the keys of a 64-bit key measured 1 millimeter. Let's say that we had each one of these physical keys was 1 millimeter in length, and we laid them all alongside each other. For 64-bit, how big would that total length be? The width of Napier's campus at Merchiston, the width of Edinburgh, 6 miles, the distance between the Earth and the Moon, about 93 million miles, or the width of the solar system, or the width of the Milky Way. Okay, so we have 2 to the power of 64 keys, and if we had physical keys, each of them were 1 millimeter, how long would it actually be? Well, amazingly, it would be somewhere between the size of the Milky Way and the universe. In fact, it would be this long, somewhere between the Milky Way and the universe. So we're dealing with extremely large numbers. Okay, so now let's look at cracking the code. It is important that we understand how secure a code is, because someone might want to decrypt it. So at an early stage it is important to define how secure it is. So in this section we'll look at cracking the code. There are a few different methods that can be used for this, and one method is where Eve knows the mapping between plain text and the ciphertext. So in this case, the encryption has happened, and she knows that that mapping is always the same, even though that she doesn't actually know the key. She can then obviously replay that back to Alice, and Alice would think that it possibly came from Bob, and because it was actually encrypted. And this also, it is if there's a mapping between a certain word and the encryption, the ciphertext, it may be possible to actually find out what the key is. Another typical method is where Eve does an exhaustive search. In this case, she has managed to get the ciphertext and then tries each of the keys within the key space until she eventually ends up with something that looks like a message. So in this case, she's actually, through exhaustive searching, actually found the message. The more keys that we have, the longer it will actually take. Another method is the man in the middle, or in this case the Eve in the middle, where Eve has managed to get herself in between the communications. So Bob thinks he's communicating directly with Alice, but is actually communicating with Eve. Eve is then communicating with Alice. So there are two communication channels set up, one between Bob and Eve, and the other between Eve and Alice. So in this case, there are two keys involved. Eve generates one for Bob's communications, and then generates another key for Alice. So the encryption happens, Eve then decrypts it, can read the message, and then modify it if she wants, then re-encrypts it with the new key, and then sends it to Alice. The man in the middle attack is actually one of the most difficult to overcome. Another method that Eve might use is the replay system. In this case, Bob has sent a message. Alice could then send the same message back to Alice and replay it exactly as it. This might not seem a great difficulty, but if we can imagine that if this was a bank transfer, then some money was being sent and the bank was replying back with a message saying OK or reject, then it might be possible for Eve to replay back one of those messages to Bob to pretend to be the bank. We can also have cut and paste. If Alice knows parts of the message and how they're built up, it might be possible to build the message back again from the bits of the ciphertext. So in this case, she has taken bits of ciphertext, pasted them together, and produced a completely valid ciphertext. Along with that, it might be possible for Eve to analyse the encrypted text in great detail, or the reply that she receives back from Alice, and then analyse how it was encoded. So an example of this might be for Eve to send an email to an encrypted server. Okay, so one of the most basic methods for analysing the strength of a code is related to brute force. With brute force, Eve can possibly try all the keys, so it is important that we understand how many keys are actually possible for the number of bits that we use in the key. So we can see in this case that for an 8-bit key, we only have 256 keys, not too difficult. And as we increase, 56 bits is one of the most significant. And the reason it's significant is that one of the most important encryption algorithms, DES, uses a 56-bit key. So in this case we have 7.2 and 16 zeros is the number of keys. And the more bits that we have in our key, the larger the key space will actually become. So with brute force, as we said before, Eve tries all the keys and eventually she finds something that looks like a message. She might have several of these and she can actually pick off which one looks most like the original message. And the key thing is that this all takes time. Obviously it's not going to be done manually because it would take Eve a long time to search through all the codes in hexadecimal or base 64. So this is typically done automated with a computer program. Okay, so let's take an example. We'll take a fairly difficult key of a 64-bit key and see how long it will take Eve on average to find the key. It has 1.84 and 19 zeros, or 18.4 million different keys from there to there. Hopefully the key isn't at the start and will be somewhere near the end. So the thing is that we need to determine how long it will take by brute force to crack it. Okay, so let's say that it will, on average, it will take 0.9 times 10 to the 19 goes. And we take a fairly fast computer with a 1 gigahertz clock, so it checks one time every billionth of a second, or 1 nanosecond. If we do the calculations, this times this, we get that the code will be cracked with inside 9 billion seconds, or 150 million minutes, or 2.5 million hours, or 285 years. So that seems a fairly long time that we have for the message. Obviously every message has a certain time that it needs to stay secret. So in this case 285 years seems a reasonable amount of time. Okay, so let's say it takes 285 years now. One thing that we do know is that computers typically increase their performance every year. So let's say that our computer systems are doubling in performance. So this year it takes 285 years, next year it only takes 140 years. And then what we can see is that after only 17 years, we are down to 1 day. So something that took us 285 years today, in 17 years' time, because of the improvement in computers, only takes 1 day. And the worrying thing for this is that DES was developed 30 years ago. So we can see that computer systems have improved greatly since then. So we can see here that we're only actually taking 20 hours to decrypt what took us 285 years. Along with this, encryption is one of the most scalable applications when it comes to parallel processing. What we can do is that we can split the key space, in this case into two, and we can give half the keys to one computer and half the keys to the other, and that way we'll take half the time. If we had 4 computers, we would take a quarter, 16 computers will take a 16th of the time, and 256 computers will take 256 of the time. So we can see now that with one processor it might take 104,000 days, but with an array of 1 million computers, so if we had a processing array, it can only take 2 hours. And then if we look at that in terms of increasing computing power, we can see that very quickly now, just within year 5, we go from thousands of days down to several hours. And to show the problems with the DES code, the Electronic Frontier Foundation decided that it would build an array of processors. In this case we have 1800 processing elements, and they eventually cracked 56-bit DES in 2.5 days in 1998. And now, for less than $10,000, it is possible to crack the 64-bit DES with this system, the Copacabana. Encryption is obviously a challenging area, and RSA Labs have posted several challenges to the community to be cracked. So we've seen there that in 1997, 1998, DES was cracked within 2.5 days, and then DES 3 was cracked in 22.5 hours, and the 64-bit RC5 in 2002 was cracked within almost 1800 days, of which 83% of the key space was tested. Currently, a 72-bit challenge has been posted, and many people are working on this. The distributed.NET works in a way that it is possible to download a process which runs when the screensaver starts. So in this case, the screensaver is starting and stopping. So we can see here it goes up to maximum CPU utilization when the screensaver is on, and in this region it's computing some encryption keys related to the RC5 algorithm. We've stopped the screensaver here and started it back again. So it's possible to create a massively parallel processing system that can search encryption keys. Along with this, there are some exceptional computers in the world. One of the largest is the Blue Gene system, which is used by the Department of Energy, and it has 131,000 processors and is nearly 2 million times more powerful than a desktop computer. Redstorm also is a fairly powerful machine with 126,500 processors. Another fundamental area that we need to understand is the difference between block encryption or stream encryption. With block encryption, we typically take the plaintext or the data that we want to encrypt, and then we split it up into a number of blocks. So in this case, we've taken 64 bits at a time. So we take 64 bits at a time, and then we apply a key to it and create cipher blocks. The cipher blocks are then transmitted together as or stored as a single cipher block entity. Typical block ciphers are DES, 3DES and AES. Sometimes what we want to do is to encrypt a stream of ones and zeros as they come in, and this is the typical method which is used in wireless communications, where we have a stream cipher. In this way, we have a key. The key has some random seed to make it different, and it goes into an algorithm which generates an almost infinitely long key that can go on forever. To keep things simple, we take the plaintext or the data, we exclusive OR each bit one at a time, and we get the output bit. So this is the advantage of being fairly quick. The algorithm that we'll see is the RC4 algorithm, which generates this pseudo-infinite key. Okay, so the first method that we'll look at is private key encryption methods. With private key encryption methods, we use a single key to encrypt, as we have seen. The major problem that we have, and as we've seen, is that it might be possible for Eve to be able to play back an encrypted stream. So in this case, it is possible for Eve to take the cipher stream and play it back to Eve as if it was an encrypted message. So what we typically do is we add salt to the encryption. And with salt, we can see here, we take our block, we encrypt it with a key, we take another block and we encrypt it. Typical block sizes are 64 bits for DES and 128 bits for AES, Randall. What we do though is that we add salt to the key, typically known as an initialization vector, IV, and then that changes the encrypted block in some way. So as long as both sides, Bob and Alice, know what the IV vector is, they just apply it and it is possible for them to be able to decrypt it. Then the same block will have a different encrypted block, so it's not possible for Alice to play it back. An enhancement on this is to use what's called cipher block chaining. With this, we take our block, we exclusive OR our block with our initialization vector, add the key, then we take the block from the last time, we exclusive OR it with a new block, and we get a new encrypted block. This, taken from Wikipedia, shows how this happens. We can see here that an image, which is encrypted with one of the most robust private key encryption algorithms, AES, we can actually still see the object, and this is because of our problem of recurrent blocks having the same pattern. But we can see here, if we use this method, then when we encrypt this image, then it's very difficult to see it. One of the main methods which are used in private key is DES. DES uses 64 bits and has a 64-bit encryption key, but unfortunately if the bits aren't actually used for the encryption. So it is a 56-bit key. So it is fairly insecure in terms of decryption, and it can be typically cracked in a short time. An enhancement to this is known as 3DES. With 3DES, we use 3 keys. One to encrypt the message, another key then decrypts it, and then a third key encrypts it. Typically, we keep key 1 and key 3 the same, so that it stays compatible with the original DES. So this gives us a total key size of 112 bits. Another algorithm which is often used is RC2, which has a 64-bit block code and a variant key size from 40 up to 128 bits. It also has an initialization vector. And now AES Randall is seen to be one of the best encryption methods. It can use variable key sizes from 128-bit to 256-bit with a 128-bit blocks, and has now been standardized by NIST. So if we now look at an example of this, so this is 3DES. It just takes a little minute to load the page. Once it's loaded, it should be fine. So this implements the 3DES algorithm. We put some text in. We apply our key, 1, 2, 3, 4, 5, 6, 7, 8. Encrypt it. And we can see here, this is our encrypted stream, and then just as a test, we should be able to get our original text back. go back, and now we look at RC2. RC2, we just put in some text. We look at our encryption key, we'll just call it test, and we can see here there's encrypted stream, and that's the decrypted text to test. We can find out actually what the size of the block is if we go for a very small message, and this is the smallest block size, and if you counted those, then you would find there's 16 characters in there. 16 characters relates to 64 bits, as each of these hex characters is 4 bits. So this fills up one block, and we can see the ciphertext block from it. For AES, Advanced Encryption Standard, or RAINDAL, then we have one of the most up-to-date encryption methods. We'll just go for test and test. We encrypt that. You can see there it has a larger block size, and we should find that that is 128 bits. So it takes 120 bits. There isn't enough bits in here, so that it pads them with some null bits. Okay, so the 3DES, RC2 and AES RAINDAL are three of the most popular private key encryption algorithms. When it comes to stream encryption, RC4 is one of the most popular, and RC4 is used in wireless communications, and especially in web, and also for most secure communications that happen over the internet, and that's with SSL. With RC4, we take our IV, an initialization vector, or salt. We take our key, generates a pseudo-infinite stream. We take our data stream, and we do a very simple exclusive OR, and end up with a cipher stream. So we can see here 0, 0, 0, 1 gives us 1, 1, 1, 0, 0, 1, 1, 1, 0, 0, and so on. Okay, so the next thing we look at is the encryption keys themselves. The encryption key, we can assume that we have a large key space for our keys, but unfortunately in many applications the key space is actually limited. So we might actually be using a very large key space, but the number of actual keys that are actually possible is actually fairly limited. This type of system is open to a dictionary attack, where an intruder could search through various dictionary words and generate encryption keys that could be tried. So Eve doesn't have to look through the whole key space. And this measure of how good the key is known as key entropy. And key entropy defines the actual real size of the key. So if an encryption key itself is generated from, say, a keyword or a passphrase, it's actually been shown that each English letter is only worth about 1.3 bits per character. So an 8-character word only has a key strength of about 10.4 bits. So you can see here that if there was only 256 phrases that were used, it's only equivalent to an 8-bit. So we might be using a very large encryption key space, but only using 8 bits of it. For 1024 phrases, it's 10 bits. For 1,000,000 phrases, 20 bits. So it's something to be, it's an important factor as to how the key is actually generated. In wireless communications, for example, the web key was based on a passphrase, and it wasn't too difficult for someone to go through all the typical passphrases and generate a number of keys. Okay, so one problem that we have is how Bob and Alice send their secret key without Eve finding out. Okay, so the dilemma is, how do they send their keys without Eve listening? This problem was solved by Whitfield Diffie, who came up with the DiffieHellman method, and is now one of the most widely used methods for passing secret keys. It is used almost everywhere on the internet in many applications. And with the DiffieHellman method, the mathematics behind it is that Bob and Alice agree on values G and N. Bob generates a random number, Alice generates another random number, then Bob does a simple calculation to generate a value A, and Alice does the same. Bob then sends A and Alice sends B, and even though Eve is listening to A and B, it is extremely difficult for her to actually find out what the derived keys are. So in this case, when they do the calculations, key 1 and key 2 should be the same. As an example, we can see here 5 and 4 are the values, generate 3 and 4. The value of 5 gets generated here, 1 here. They pass those values and they end up with the same key. If we look back here, we should see an example of DiffieHellman. Sometimes we can easily overflow a software program. So G and N here, we have Bob generated 3 and Alice 3. We have values 59 and the keys are the same. Unfortunately, Bob and Alice have chosen the same random value. So generate another one, in this case 10 and 8, calculate A and B, 12 and 14, and hopefully at the end of it the keys should be the same. So DiffieHellman allows us to be able to generate a secret key without and communicate openly without Eve finding out. Unfortunately, DiffieHellman suffers from the great man-in-the-middle attack, or Eve in the middle. In this case, she can negotiate one key here and another key here, and as far as Bob and Alice can tell, they are negotiating with each other. Another example might be in what's called DNS poisoning. In this way, Eve poisons the DNS server so that instead of communicating with Alice, which is the eBay server here, Eve poisons it so that the communication actually happens with another server. Okay, in this part we look at public key encryption. Okay, so with the DiffieHellman method, we could actually pass secret keys. But it was proposed that it might be possible to create an algorithm where we can apply a key and then use a different key to reverse that action. And this was solved by Rivest, Shamir and Alderman with the RSA algorithm. And with this, we select a public and a private key. The mathematics behind it is that we take two prime numbers, and prime numbers are actually fairly difficult to factorize for. So we take values A and B and we work out a value of n. The value of n is used as part of our key. In this case we have n here and we have n there. So E is then chosen. We find out A minus 1 and B minus 1 and we multiply them together, and then E is chosen so that it does not have a common factor between E and this value here. Then the public key becomes EN, and the private key is then calculated with this equation here. And it's with these two keys that we can actually encrypt with a public key and decrypt with a private key. So it works. We generate these two keys. It can actually take quite a while to generate these keys, but either side has a public and a private key. One is used to encrypt, doesn't matter which one, and the other is used to decrypt. So when Bob sends a message to Alice, Bob gets Alice's public key. He then uses that to encrypt the message, and the only key that can now decrypt this message is Alice's private key. He sends this. Eve should not be able to decrypt it. She then uses her private key and then can decrypt the message. In that way we can keep the communications secure. The third encryption method is one-way hashing, and with one-way hashing we have no reverse action. We take, in this case, some plain text, we put it through our hashing algorithm, and we cannot reverse the action, so it creates a hash signature. So in this case we take the text, and Eve cannot work out what the actual original text actually was. Typical algorithms are MD4, MD5 and SHA1. It's typically used, as we'll see in the next unit, to create digital fingerprints and in secure storage of passwords. An example here is with the Windows login authentication, where we take a password, it is then hashed with MD4, and then it produces the hash function. Another application is in the Cisco password storage with MD5, where we can create our secret password, and when it is displayed it is shown in an MD5 hash format with some salt. Unfortunately, hashing suffers from dictionary attacks, where it is possible for an intruder to generate a whole dictionary of words and the equivalent hash, and then looking up the hash to tell what the original message actually was. So to make this more difficult, many users change certain letters to make it more difficult to search through a dictionary. With hash signatures, obviously there is a finite number of signatures, so what can happen is a collision, and a collision is where a different message creates the same hash signature, and this, it might be possible to have what's called a collision attack, where an intruder creates another message with the same hash signature. More complex than this is that an intruder might be able to create the same hash signature with a similar context for the message. In some way the message has some of the information of the original and creates the same hash signature. And the most difficult, of course, is a full context where the intruder has managed to create the same hash signature and the message itself has the same context. And it was shown fairly recently in 2006 that the MD5, it is possible if you store hash signatures, and it takes less than a minute to actually produce the same hash signature. The calculation for this is for a 50% probability of a collision is the square root of the total number of signatures. So in the end it ends up 2 to the power of n upon 2. So for an MD5 128-bit, for a better than 50%, then if we store 2 to the power of 64 signatures, we'll have a better than 50% chance of a collision. One application of public key encryption is with encrypting disks. As we'll find later on, private key encryption is still one of the most widely used encryption methods, and public key encryption is typically used for the authentication part. But one application for the RSA method and public key encryption is encrypting disks. In this case, when we use the Microsoft EFS, encrypted file system format, when we want to encrypt files or folders, the system itself creates what's called a digital certificate. The digital certificate has both a public and a private key stored in it. It is important that this certificate is kept on the system, because once it is lost, then it is not possible to decrypt the encrypted content. So the certificate itself shows that we have the private key on the certificate. So one of the keys is then used to encrypt the content on files or folders. Once it is encrypted, the only key that can decrypt it is the other key, in this case the private key, and is able to get it back again. So it's this certificate here that stores these keys. We can see here that we're using 1024 bits RSA. To encrypt, we select a folder, we select the advanced options on the properties, and then we encrypt, after which we should see the folder turn green and all the subfolders should be encrypted too. This then creates a certificate, and the certificate is stored on the machine. Often this certificate can be backed up onto a USB drive or onto a network drive, so that if there is a crash on the machine and the certificates are lost, then it's possible to get the certificate back again and to decrypt the contents. With the increasing usage of mobile machines, it is important that important files are kept secure. As we've seen, the private key encryption method is fairly processor intensive, and an alternative method of encrypting is the PGP encryption. With PGP encryption, an encryption key is created for each session or for each email that is actually sent. Then this key is then used to encrypt the content. So Alice has no idea what this key is at all at this point. Then Alice's public key is then used to encrypt the secret key. So we now have two things: the encrypted content, which was encrypted by the secret key, and Alice's public key is then used to encrypt this key. So now, on the other side, the first thing that Alice will do is to use her private key to unlock the secret key. Once the secret key is unlocked, she can then use a private key, secret key algorithm to decrypt the encrypted, the cipher text. So in this way we can use private key, which is fairly fast, and we can generate the keys on spec without using DiffieHellman. But then we can use public key just to encrypt the key that was used to encrypt the message. So no one will be able to decrypt this main message because it won't be possible for them to unencrypt the secret key. And this was the genius behind the PGP algorithm created by Phil Zimmermann. So conclusion to this is that we've seen that key interchange happens with DiffieHellman, and that is used to generate a secret key, and we typically use private key encryption methods such as DES, 3DES and AES, which are fairly fast in their encryption. As we'll see in the next unit, public key encryption is typically used to authenticate the sender and the recipient.